Okay, so I'm Marcus. I work as a data scientist at Tenfifty. And today I have been working for exactly 1 year, I think, on the day. And I'm here to talk about a project that I started working in on day 1. I think I can say without lying. And so to set the scene, about a week ago, or exactly a week ago, a Chinese company called Tencent published this paper where they collected 18 million images as a data set for computer vision. And that's a lot of data. And if you think about the progress that you've seen in computer vision for the last few years, which has been quite remarkable, you can attribute at least part of that to this just simple idea of bigger data. But what if you don't have 80 million data points? What if you just have 1,000? Is there any point in doing something if you just have 1,000 data points? So that's what we're gonna look at today. And when we say computer vision, we normally think about things like what's in an image, or can you say where this object is in the image, which pixel corresponds to which class, or even more specifically, which pixel corresponds to which instance of this class. And the problem that we're trying to solve, the reason why we're doing this, is that we wanted to annotate news broadcasts. And so we wanted to get both hard-coded subtitles and these typical kind of broadcasts text boxes. We didn't want to get text in the background, like that one, or logos or timestamps or anything. We're going to do this in 3 stages. So first we're going to find the regions of interest in the image, just the ones we showed before. Then we're gonna perform OCR to get the text. And then we will have kind of flowing text, we will take maybe 1 frame a second or something. So the same box, the one up there, for example, might appear consecutively. So then we need to deduplicate, determine like, is this word the same as the word that came the last frame? Is it misspelled? If it's misspelled, if we had 2 different spellings, which one is the correct one, and so on. But today we're going to focus on the first part of this, so just extracting the boxes. And first we need to decide which method are we going to use. And the answer is not always machine learning. I know that we're at a machine learning meetup here, and today the answer happens to be machine learning, but it could be something else, right? So we also considered, can you do like pattern matching? Or can you use the gradients and look at if you have high gradients in vertical or horizontal directions, you could say that these are lines that could be a box. So we tried both of these first. Turns out it doesn't work so well. Maybe it could. In our case, it didn't. So machine learning it is. And when you say machine learning for visual learning or computer vision, you typically talk about COMNETs, so convolutional neural networks. And the whole idea is that in a picture, you have translation invariance. So it doesn't really matter if the dog is in the upper right corner or in the middle. Like it's still a dog, and probably it's going to look about the same. So rather than looking at the whole input just at one, we're going to scan through the image, apply a kernel, and in that way you can use this translation invariance. And most forms, most architectures for computer vision could be thought of as 2 steps. So first you have an encoder where you take your input image, you transform it into some kind of latent representation of this image, which typically will have a much lower resolution, but a much higher channel count. And channel, when you start, you might have red, blue, green, so RGB. You might have one channel, just grayscale, which is what we've been using. What the channels are in your latent representation is less clear, which is why it's called a latent representation. But once you're there, you can either have something like a fully connected feed-forward network, perform classification and say, okay, there's a cat in this image. Or you basically backtrack, you reverse what you did with the encoder, and you go back to a mask for your image for semantic segmentation. And often you will do these either jointly, you can train them together, or you train on one task first, you throw away the decoder, you reuse the encoder, and then you train for a different task with a new decoder. So if we think about what we want to do now, we want to find boxes, right? So it seems obvious that we should use object localization, that's what we want to do. But we actually, it is what we're doing, but we go through segmentation. So we're taking a segmentation approach, and to understand why we do this, we need to think about, what are the strengths of respective approach. So when you have an object localization model, you can do things like separate multiple connected instances. If you have a dog, you can say that these are separate dogs. This is something you cannot do in a semantic segmentation. If you're doing instance segmentation, you can. But then you find many of the same problems you have for object localization. And you can also find partially visible objects. So say that you have a horse. I like using animals as examples. And behind this horse, you can see a horse head sticking up. And a human could say, well, it's probably not just a horse head, right? It's probably a whole entire horse. It's just hidden behind this other horse. And you can do the same with object localization, but for semantic segmentation, you're just predicting, one class. So this is information that you lose. Speaking of lost information, okay, we're back. And it's also much easier to annotate because you just drag a box around your horse. You don't need to, go through and outline on a higher resolution.
I think you had a question.
Oh.
No problem.
Okay.
Go ahead. No, go ahead.
How can I distinguish? How can I will come to the conclusion when I have to use object and when I have to use segmentation techniques?
Yeah, great question, because if you say that you want a box, which we want, you would think object localization. I would say when these strengths for the localization model is important. So say that you want to predict, it's important if you have several objects that you distinguish between them. Say that you're doing computer vision for an automatic car, self-driven car. It might be important to know that this is not just one very big person, it's actually 3 different people. I would say that's one of the things. And also then, in this case, and I'll come to that, that's the reason why segmentation makes sense for us. But if you're looking at the horse, it's quite time consuming to annotate for segmentation, whereas localization is much easier. So it might be easier, you might have bigger data sets and so on. And for, often it might not matter the strengths of the segmentation. So yeah. But I will very shortly describe why we used segmentation in this case. So the strengths of segmentation is that it's conceptually more simple. You can directly predict your mask, your desired output, Whereas in an object localization, you need to figure out, okay, there can be several objects. How do you know how many? How do you know, often you will use so-called anchor boxes. So basically you say, here are where I think my desired boxes could be. And you might have hundreds or thousands of these. You can be slightly smarter and say, okay, we look at the training data, we generate a prior over where boxes are located or how big they are. So, but you're still dealing with a lot of boxes. And there are techniques where you predict these directly. But it is another, something you have to do, a complexity. And then you also need to deal with, if you're predicting boxes, you might predict several boxes for the same object. And then the question comes, is this the same object, or are they actually different? Is it a horse behind a horse, or is it just one horse? I wrote faster star. This says we have tried both, and in a few different architectures, and we have found segmentation to be generally faster. This might not hold true in general, but and it's also easier to troubleshoot. So, and we will see this later, that you can get a pretty good idea how the model is training and how it's behaving, because you're predicting heat maps basically over your input image. So back to your question. In our case, these strengths of the object localization model, they're not very important. So we don't really care if you have multiple connected objects. We don't mind if we put them all together to one. That's fine. And we're never going to have partially visible objects, because the text box is always going to be on top, right? And for the specific case of rectangles, going in between the annotation for a boundary box, which is just a rectangle, and the segmentation object, which are the pixels, is very easy, which is not generally true. So it does add another step. Given the predicted mask, we need to figure out, okay, where is the actual box? But that's pretty easy to do. You basically find the pixel clusters, and then you just say, okay, what box do I need to actually enclose these pixels? So I think the theme of today in general was low data, right? And the big thing, if you look at big data and small data, and I think David is going to talk more about this, but when you don't have a lot of data, you need to provide instructions for the model. You need to put constraints and say, okay, the solution is somewhere in here, right? It's still machine learning, but we can't learn quite as much because we don't have as much data. Whereas if you have a lot of data, you can say, okay, be free. You can learn that you can figure out the constraints on yourself, on your own, by yourself. And so in this case, it's going to mean using smaller models. We might not use a ResNet 101 for the encoder, which is a pretty big model. Calling pre-training an encoder on a different data set or task. A low data technique might be a little bit of a lie, because it's something you would probably use it even if you had a lot of data. It's something that's very commonly used for visual learning. Data augmentation is when you corrupt your input images in some way. It might be changing the lighting, changing the color space, translating or cropping it or so. And then this last point is a bit tongue-in-cheek, but it's not completely stupid, because normally the performance of a model will scale roughly logarithmically with the number of data points you have. So every data point you add is less valuable. So when we're looking at 500 data points, it's quite easy to double that amount. When you're looking at 18 million data points, it's quite difficult. This is something we did in order to speed up the annotation of the data. So rather than sitting down in one session and just saying, here's my coffee, here's my Jolt Cola, now we're going. We annotated like 100 images or something, started on a small scale, trained a model, predicted on the next 100 images, and then you can just correct. So in the beginning, the model might not be very good. You need to correct a lot, but it's still faster than doing it yourself. And then once the model gets better, it will be faster and faster. And this is the effect of doubling the amount of data, basically. So going from 450 to 890 data points, which is looking at the validation losses. It's not great, but it is significant. We also thought that in this particular case, we could actually generate synthetic data pretty well. You just take any random image and you make up the headline of today. It's a text box like this. We're quite hopeful about this technique. But as you can see, while the loss on the validation set, so what we've done here is we are comparing two models, one which has been trained from scratch on real data, and one which has been trained on synthetic data first and then fine-tuned on real data. So those are the two models we're comparing. And you can see that the one that's been trained fine-tuned from the synthetic model it performs better early on, but in the end there's virtually no difference. And the second thing about data augmentation, you can be quite sophisticated in what you do. We didn't want to clip any text boxes. That would probably not be a problem, but could potentially be. So we have just added mirroring, contrast reduction or increase. And this is how the image looks like when you feed it to the network. So we have grayscale, resized it to 256 by 256. And this is how it might look like if you add data augmentation. And the same kind of graph for this case. If you're optimistic, you might say that the augmented model is slightly better. It has a slightly lower generalization gap, and it is something we're using. But I think you could also skip the data augmentation and sleep pretty well at night.
Could you just explain which one is which?
Yeah. Okay. So you need to be pretty optimistic. So the red line is the red and the green are for the model that's trained when you have data augmentation on the training set, so not on the validation set. And so what we're really interested in is the red line and the orange line. And so this is the loss on the validation set during training. And so this is where we end, roughly. This is where we stop training and we're saying, okay, we're done. It's not exactly what you're looking for, the loss. I mean, you're looking for how many on the validation set do we get correct, whatever that definition might be. But we found the loss to be a very good proxy for that. So you could look at the loss and say, okay, this is how good the model is at this task. So really what you want this line to be as low as possible, then you're happy. And if it's close to this line, you're also happy, but it's perhaps not as important. And so in this case, we would hope that the red line was a lot lower than the orange line. This is clearly not the case. It's maybe, possibly, a little bit lower, but not by much.
Can I ask the peaks or the corresponding, have you done an analysis on what they Are there specifically hard pictures in the dataset?
No. To answer the first question, no, we haven't looked at it. It is interesting, and it's also interesting that it doesn't look like there is some periodicity to it, but it's not strictly periodic. So that's something. If you had problems with the model in the end, if you found that it just doesn't handle this very well, then yeah.
Are you treating it as a classification problem, or what is the actual output from the model?
So the output from the model first is a mask. Basically, you predict. We started with a picture that was 256 by 256 by 1 for a grayscale, and then we predict something that's also 256 by 256 by 1. In our case, we just have one class. So the only thing we're predicting is this region, is this pixel interesting to us? Do we want this pixel? And then we perform the steps shown before, where you take these pixels, you cluster them, you enclose them in boundary boxes and say, okay, these are the boxes we want.
And the loss is then?
And the loss is, before that, the loss is on the segmentation stage. So it's root mean squared loss based on the pixels. Yeah, so then we haven't done the boundary boxes yet. And I think, I will mention in the end that you could go further and talk about actual metrics about how your model is performing. And there is, apart from the peaks, there is one interesting thing with this, and it's if you look at the validation curves here, both the orange and the red. In the beginning, they seem to reach a kind of a plateau, and we can see exactly why this is. So this is a video of we have an image from the validation set. We're going to show the heat map or the prediction that we're making. Blue is 0, red is 1, and the white is in between. And we'll see that the first thing the model does when you're training it is just say, okay, there are no boxes. That's the best. If I can't be very specific, that's the best thing I can do. And then eventually it starts learning something useful. Comes eventually. It's all good things. And I think sadly this video doesn't freeze at the final frames. You can see exactly what it was, but you could see that there was some flux in this, right? It wasn't quite stable. So you could imagine that even if it's not just a certain image, it could be a certain image in the validation set. It could also be that it's not quite stationary. And for the validation, so we've been looking at loss. It's not exactly what's important in the end. The important thing is do we get the text and do we get as little as possible or something else. And you could consider some less unrigorous metric. You could either look at the segmentation task and say, okay, out of the pixels we predict how many are correct, what's the F1 score. You could also look at the boundary boxes that we construct. You can compare them to the boundary boxes we would construct for the target input. And if you do object localization, a common metric is mean average precision. So you look at the precision recall curve, and then you average overall recalls, and then you mean overall thresholds you could use to construct the boundary boxes based on your prediction. Something like this. But we have found loss to work well enough. So it might be something that we do in the future, but but it's not something we have. But if you will look at the performance on the validation set ourselves, is that correct? No, it should be, so we have about 99% recall. So most of the pictures that actually are text boxes we get, and then around 98% for the precision. So we do have some cases where it's not a text box, but we say that it is. And just to wrap things up, we're going to look at how it actually looks like, both the prediction output and then the text box that we construct. And there is a slight delay because we only predict for, I think, once a second or something, and the rest is just staying there from the previous prediction. But we can see that that we have managed we managed to filter out the logos and the timestamp there, and you will see soon that we also don't pick up on the microphone text SVT. And it's quite good granularity as well on the prediction, that it's not just predicting a box, it's predicting where the text is in the box. And it also works if you have subtitles that have no box. You still get a pretty good prediction.
So how much annotation did you need for this? How much training data?
Yes, so right now, what we've seen here is 891 data points in the training set and 51 in the validation set. And if I would need to annotate the same amount now, say that I had the images already and I just needed to annotate that, that might take around a day, I think. But that's given that you have the model, you can use that to predict in the beginning and so on. Yep. Yep.
You say you filter out logos and microphone and so on.
Yeah.
How do you do that manually?
No. So that's just in the data annotation stage. We say, okay, given this image, the only true part, the only boundary box that we want in this image is the text box. And so in this case, we have a few different broadcasts. I think this was SVT report. It's 1 out of 10, I think, in this training set. And then we actually use the model on around 50 different ones. It typically generalizes quite well. There might be cases where broadcast is very different, in which case we might need to add some training data for that. But so in this case, it's just saying, okay, that's not a box. So it's basically doing nothing with it. And then you can get into interesting questions, say that you don't label this as true. Might this mean that the model learns that this is nothing and then it gets something that's similar but that we actually want? Is it possible to have a scenario where not labeling this is destructive? It doesn't seem so, but it's possible.
For example, if you have a logo which is a box.
Yeah, exactly. It might be SVT. They're talking about their own. They had problems during Christmas, something. Yeah, and then the question is, do you miss it then? And I haven't seen it, but you can never say never. Yeah.
Since both the synthetic data and the augmented data didn't do a lot of difference to
Yep.
the result, what was your actual result that improved the fact that you had so little data?
I think in general, possibly the task is easy enough. Possibly the architecture is doing a lot of heavy loading. Like just using a convolutional network is already putting quite a heavy constraint on your model. Like you're saying quite a lot about what you expect your input data to behave like. So my hypothesis is that given a huge data set and a big enough computer to work with it, a feed-forward network could do pretty well at visual learning tasks. Probably still not as well as a ComNet, but especially when you're working with And also 891 is not, it's not a tiny data set, right? I think a rule of thumb is, say, 5,000 data points per class. So what's also helpful is that we have one class. I think if we had 10 classes, we might have a problem.
But did you also use a simpler topology?
It is slightly simpler. We showed just what a normal convolution is. And typically you transform, say, a patch of 3 by 3 both from your input channels to your input channels at once. And so we use kind of a factorized version of this where you do it in 2 stages. And this means that you, for one, if you look at the complexity of the calculation, you turn a product into a sum. So it's a lot faster. And then also you reduce the expressivity of the model a little bit. So yeah, so simpler model. It's quite similar to something you might use on a mobile phone. So it's in that sense, it's not that powerful. Yeah, thank you all very much. Thank you to Telia and Squid for hosting this.